share my slides. Can you see it?
Yes, I can see it. Okay. Give me a moment. Okay. Yep. So today we have Ken Sakayori Yuri, who just started his postdoc in Bologna, I think. And he's going to talk about the categorical analysis of the pi calculus. So please start.
Okay, thank you for having me. Yes, I'm at the University of Bologna, but the work I'm going to present today is the work I did back when I was in the University of Tokyo. And the talk is based on joint works with Takeshi Tsukada. Okay. Wait, slide doesn't move. Okay. So this talk is about categorical type theoretic correspondence for a variant of pi calculus that is not limited to race or deadlock-free processes. So in this sense, it's different from the well-known Carry-Hard correspondence for session-typed calculi. And our pi calculus that I will present is similar to the pi calculus proposed by Milner, in the sense that we use a sorting system that is similar to the one Milner used. So why are we interested in establishing such a correspondence? Well, one reason is because the process calculus that corresponds to linear logic has a limited expressiveness. And in fact, one of the persons who established the correspondence, namely Wadler, said that it will be a limited value if if linear logic will be of limited value if it only models deadlock-free processes. And he asked a question saying, are there extensions that support more general forms of concurrency? And so this talk is not about logic and the category theory, but so, well, I would say that my work is trying to answer this question and giving a foundation to a more relaxed version of pi calculus. Okay, and today's another main topic will be about the weakness of our correspondence. So I will show you a result saying that a variant of pi calculus corresponds to a certain categorical structure, but we are not completely satisfied by our results. And I will talk about the weakness or the defect of the correspondence. And this is a seminar, and it's not something like a PhD defense where I have to predict my work. So I thought it might be a good idea and a good opportunity to honestly speak about the problems we have and receive some feedback from bright people listening to my talk. Okay, so let me start by reviewing the categorical type theoretic correspondence for simply typed lambda calculus. So it's well known that simply typed lambda calculus corresponds to Cartesian closed categories, which is category with products and function spaces, I mean exponentials. And what I mean by the correspondence is that if m and n are beta eta equivalent, then we can show that in all the Cartesian closed category, their interpretations are the same. And in fact, the opposite direction can be said as well. And if the interpretation is the same in all the Cartesian closed category, then m and n are beta eta equivalent. Okay, moreover, lambda terms modulo beta eta theory forms the initial Cartesian closed category by thinking objects as types and morphism from A to B, a lambda term modulo beta eta equivalence. So what we'd like to do is to establish a similar result for the pi calculus. And to do so, we look for a categorical structure sufficient for interpreting the picalculus. And adjust the syntax and the equivalence relation of the picalculus to obtain a solid correspondence, like soundness and completeness. So now the question is, what kind of categorical structures correspond to the constructs of picalculus? Okay, our starting point is to consider picalculus as a process passing calculus instead of name passing calculus. So this shift of view, thinking that picalculus as a process passing calculus has been observed in the early work by Sangiorgi, where he connected higher order picalculus with picalculus. And there, the key idea is to regard an input process as a function located at A, so it's of which I will write like this, and regard output actions as a function application. Then the usual reduction, which is usually considered as A transmitting the values Y, and this process is receiving that value and then running its continuation, can be seen as this kind of reduction, where instead of passing the name, you pass the function to the opposite side, and then you do a beta reduction. So our idea is to look for categorical structures that models abstraction and application, that is a functional part of the picalculus, and address assignment, which connects a location with a value. So to do so, we use a categorical model for the lambda computational lambda calculus, namely closed Fried category, to model the functional part of the picalculus, and we use a categorical structure called compact closed category to model the connection part, because compact closed category is a categorical structure that is used to model like port connections. Okay, so from now on, I will first, okay, so this is the outline of my talk. First, I will talk about the categorical type theoretic correspondence. Then I will talk about the weakness of the correspondence in the latter half of my talk. Okay, first I'm going to start from the syntax side and show you the variant of picalculus we designed. So our target calculus, which we call PyF calculus, I think F comes from functional or something like that. My course named it, so I am not 100% sure why we named it this way, but it is a subcalculus of the asynchronous picalculus. So we have the usual nil process, output action, and parallel composition, replicated input, and name creation. So it is fairly standard, but there are two things that I should mention too. One is that we only allow replicated inputs. So this reflects the idea that input prefixing represents a function that can be used arbitrary number of times. And by doing so, since we don't have the usual input action, meaning the input actions that can only be used one time, we cannot represent reference cells. So in our calculus, we're kind of working on the functional calculus in this sense, and our calculus cannot model imperative features like reference cell. And another difference from the usual picalculus is that this in the name creation. So name creation creates two names, meaning connect X and Y. It creates input and output and endpoint of a channel, and communications only occur between names connected by mu. So this is a notable difference from the standard picalculus, and by doing so, we kind of elide the nominal aspects of the picalculus. And calculi with similar characteristics have been studied, especially to figure out the connection with picalculus and linear logic, or in the study of game semantics of picalculus. So I would say this is not entirely new, but I kind of combined the observations that were already known to design a calculus that corresponds to a categorical structure. And now I will talk about types. So it has a standard IO type system, and names are either used as input or output channel. And no names can be used as both input and output, a channel with both input and output capability. By doing so, we have a duality in types, meaning that the dual of output is input and the dual of input is output. I would say the typing rule is very standard, except for this rule, which is the rule for name creation, which binds the two names that are dual to each other. Okay, so I presented so far I presented the syntax of our calculus, but there are more things to define. If we want to obtain theoretic correspondence, we need to define the notion of composition, identity process, and the equivalence for the process, so that processes modulo a certain equivalence becomes a category. Note that we cannot use the transitive closure of the reduction relation for the equivalence, unlike in the case of the lambda calculus, since the reduction of pi calculus is non-deterministic and not confluent. So, for the notion of composition, we use parallel composition plus hiding. This is a common way to define composition in logical studies of pi calculi or process calculi, I would say, or also in game semantics. And by parallel composition plus hiding, what I mean is that first we consider a judgment or this process of this type as a morphism from S to T. So there's a dual here. You can think that this type can be moved to the right-hand side, and when you do that, you have to invert the polarity. And so, and this process has this type, and it shares the type T. So to compose these two morphisms, what we do is simply take the parallel composition of P and Q and hide the name with the opposite polarity. And this gives you a function, I mean a morphism from S to U. Okay, so we have a notion of composition. So what about the identity? The identity for the type, for this type needs to be a process with this type, meaning it's a morphism from this type to this type. A natural candidate of P is a well-known process called Fodder process, which just, okay, sorry, this is wrong. There needs to be a bank here. So it needs to be a replicated process, but which receives an input at A and just transmits that data using the name B bar. And indeed, it is known that composing Fodder with a process P acts as a substitution. And since we do not care about the difference caused by substitution. I mean, we identify alpha equivalent processes. By alpha equivalent, I mean, we are also allowed to change the names that appear in the judgment. This means that composing a forwarder does nothing. So it's a right identity. And also, we can prove that composing forwarder from the opposite side also works as a substitution, meaning that it is also a left identity. Indeed, so these two equations hold for mate testing equivalence, and thus it is natural to take forwarder processes as identities. So now we have the notion of composition and the identity process. What about the equivalences? So we assembled known equational laws to establish a correspondence. And of course, when we were doing this, we already had the categorical structure in mind. So what we actually did is to think about equational laws that matches with the categorical structure. But the interesting is that we actually ended up with rules that were already known, except for this eta rule. The first rule, called the beta rule, sometimes called the generalized beta reduction, is a rule similar to the reduction relation. So C is a context, and so if C is just a whole, what the rule says is that you can equate these two processes, which is just a very simple reduction. But I should note that there is a side condition, and the side condition ensures that there is only one input that is waiting for the output, meaning that we can only equate these processes when there is no race or non-determinism. And the reason why it's called generalized beta reduction is because C is not limited to the context of this form, which is parallel composition. And this one is just a garbage collection law, so which is not interesting. And this one is the law which equates a free output with a bound output with a forwarder. And this is also a well-known law, which has been studied in the context of internal picalculus, but I'm not going to talk about the details. And the last rule is the rule that says forwarders are left identities. Okay. So now I will talk about the properties of the equational theory. So if we can prove P equal Q using the rules I just showed, okay, actually without using the eta rule, and then we can say that P and Q are weak barbed congruent, which is like the observational equivalent for picalculus. But if we use the eta rule, we can only say that P and Q are mate testing equivalent. And mate testing is a rather coarse equivalence. And this is actually the weakness of our correspondence that I will come back in the second part of my talk. Also, this is the reason why this eta rule hasn't been studied in the literature, I think. So now that I explained the syntactic side, I will move on to the categorical side. Okay, so the categorical structure we introduced is called compact closed triad category, which is just a combination of compact closed category and closed triad category. So the intuition is it can be seen as a deductive system with a unit type, pair type, function type, and a negation, with a standard rule for pairs and functions, and additional two rules, which comes from the compact close structure. And the formal definition is like this. So it's given as a triple of a Cartesian category and a compact closed category, and the identity on object strict symmetric monoidal functor with the right adjoint. And the simplest example of this structure is the adjunction between sets and the category of relations. Okay. Oh, and if you know what compact closed category is, so these two rules correspond to the unit morphism of the compact closed category and the co-unit morphism of the compact closed category. And the interpretation is defined based on the intuition I gave at the beginning of my talk, that is to consider output as a function application. So the output type, this output type will be considered as a function from T to the unit type. And in fact, what we do is to just interpret output as a function application. And what we do for parallel composition is we just consider parallel composition as pairing. And since a pairing of two unit types is isomorphic to unit types, the resulting type is also the type for the processes. Okay, sorry, I forgot to mention, but the type for processes will be interpreted as a unit type. And this is where we use a Cartesian structure. Cartesian structure is used to duplicate the type environment. And okay, input is just interpreted as okay, function located at a certain location A. And this connection of a location and a function is interpreted using the co-unit morphism of the compact closed structure. And the interesting point is that name creation is just interpreted as precomposing the unit morphism type. Okay, and with this interpretation, what we get is the soundness and the completeness result. So the soundness says if P equal Q, then the interpretation is equal in every compact closed Fried category. And also, processes modulo the equational theory forms a compact closed Fried category that classifies compact closed Fried categories. And from this, what we can say is that the completeness, which says that if P and Q has the same interpretation in every compact closed Fried category, then that means one of the categories, such a category is the syntactic one. So we get P equal Q. And these are the standard results that you want to prove when you are looking for categorical type theoretic correspondence. So what these results shows is that our correspondence is quite rigid. Okay, I'm going to skip these slides and move to the second part of my talk. Okay, so now I'll talk about the weakness of the correspondence. And as I said, the problem is related with the forwarder. So the problem of the forwarder is that even though I said that forwarders are going to be used as the identity morphisms, it actually doesn't behave as identity morphisms and for various behavioral equivalences. This law, which says that a forwarder is a right identity, is actually a well-behaved law. and we can prove this for many behavioral equivalence, but the each rule I showed does not hold for most behavioral equivalences. The only equivalence I know that satisfies this rule is a May testing equivalence, and as I said, it is pretty coarse. So to better understand why the eta rule doesn't hold, let us look at some examples. Okay, so for instance, if we take the nil process for the process P, and if we consider a nil process composed with a for-other, then this can be distinguished by this context. In fact, if you put the nil process into this hole, then the only communication you can do is a communication between this name and this name. So after that communication, you will always observe the output using this observable hole. Whereas if you put this process inside this hole, then there is a possibility that this output communicates with this input. And in that case, since this output is already consumed, you cannot observe the output from O. So they are not bisimilar. And so, well, this using nil process as a counter example is a very particular case in the sense that, well, B doesn't even occur in this process. But even if B occurs in this process, there are a lot of processes that can be used as a counterexample. And those processes are processes when B is guarded by another prefixing. So again, if you put this process into the context, then you can communicate, you can communicate using A and A bar, but if you replace B with A and put this context into, maybe I messed up. So, okay, let me say it again. So consider this process, which is CA0, and if you put that process into the context, then the only communication you can do is between this A and A bar. So you can always see the observable. Whereas if you put this process composed with a for-other, then again, there might be a communication with this A bar and A. So this is another counter example against this law. And it should be noted that the counter examples are widely applicable for asynchronous picalculus, not specific to R calculus, but these rely on the existence of race. So one can say that this is a problem that only occurs if we consider race. So if the eta rule is problematic, one can probably say that why don't you just give up that rule? But I'd argue that we cannot throw away the eta rule, because the left identity law is necessary for the term model to be a category, provided that composition is defined by parallel composition plus hiding, and the right identity law holds. By right identity law, I mean this law. Because in a category, a right identity must be the identity, meaning that it also needs to be a left identity. And I would say that these two assumptions are quite mild, because parallel composition plus hiding is arguably the most widely used notion for composition. I mean, in the setting of process calculi. Of course, one can doubt this notion, but I'd say it's really hard to come up with an alternative notion. Also, this we also want to keep this law because this law plays a crucial role when one model functions as processes. For instance, if one models lambda calculus, one encodes lambda calculus into picalculus, what you would typically do after defining the translation is to use these kind of algebraic laws to prove that beta equality is preserved. So these kind of laws are often used to prove the validity of encoding, and thus we do not really want to throw away this rule. So if we want to keep the eta rule, how can we validate the eta rule? Well, I think there are at least two possible ways to validate the eta rule. One is by restricting the language. Well, this is a common approach in the behavioral studies of the picalculus. I mean, if you add type systems or things like that, then usually you get more algebraic laws that you can prove. But if we do this, one needs to look for the semantic counterpart of the new language to retain the correspondence. Another rather drastic way to validate the eta rule is to modify the operational semantics. The good point of this approach is that you do not have to modify the categorical side. But it is unclear if this is even possible or whether a meaningful semantics can be given. And okay, and from now I will briefly discuss some existing work and a possible research direction on this approach, and then briefly talk about our investigation on this approach. So the first solution, as I said, is to restrict the language. And in fact, the eta rule can be shown to be true if there is no reason A, as I said. And this is actually what session-typed calculus do. I mean, linear logic-based session-typed calculus do. So in linear logic-based session-typed calculus, there is no race, so they do not suffer from the problem that I'm explaining. But I think there is some kind of spectrum between linear logic and pi-f calculus, meaning that there should be some calculus that is race-free, but more expressive than linear logic. But what I don't know is whether we can capture that kind of language using category theoretical notions. And I think this would be an interesting research direction, but I haven't looked at it in depth. Also, another way to validate this rule is to ensure that B is receptive. By receptive, what I mean is that the process is ready to do an action on B without doing any visible action prior to that. So in the previous counter example, I showed a case where B was guarded, but receptivity ensures that B is not guarded, and you can actually perform an input right away. And there are type systems that ensures receptivity, but again, it is unclear how to categorically model these. So this also might be an interesting topic to work on. And okay, and next I will talk about the second approach, which we investigated, which is to modify the operational semantics. And I will show you that we can define operational semantics that satisfy the eta rule, but it is open to discussion if the resulting operational semantics is really meaningful. Okay, so what we actually defined is based on a very simple idea. So we may expect this eta rule to hold if forwarders do not introduce any delay. This was the key observation we had. Okay, intuitively, the above equation does not hold because the forwarder can always receive a message via A at any time and can hold the message as long as it wants. Whereas in this process, A might not be ready. And a similar observation has been made in the context of game semantics. And there it has been shown that a forwarders without delay actually has some good properties. So, but now the question is, how can we change the operational semantics so that forwarders becomes delayless? Well, okay, so what we did is based on this idea. So we disallowed process to stop while there are unguarded outputs, which means that you are not allowed to buffer messages. And this, intuitively, this captures an aspect of synchronous communications, because the reason why asynchronous picalculus is called asynchronous is because you're allowed to buffer messages. And in fact, people consider this output action as buffering messages. So our idea is to consider these kind of two transition, one doing the input action on A, and the next one doing the output action on B as a single transition in the new operational semantics. And what we actually did is, well, we didn't define a labeled transition system. We defined a reduction semantics because that was easier to work with. And so what we did is we defined the new reduction like this, which is that you can do an initial tau action, which is just an internal action, and you do the normal communications until Q has no unguarded outputs. And we defined the new one-step reduction relation in this way. And okay, so we introduced tau prefixing in the grammar. So now we have this in the grammar, but this will not have a big effect to the categorical semantics, as this is just adding a constant. And so this might look a bit peculiar, but let's see some examples. So for example, in the new reduction semantics, we can do a one-step transition from this process to this process. Because if you take off this tau prefixing, then this output is unguarded, so which means you have to consume this output. And the only thing you can do is to communicate with this input prefixing, and then now you get an unguarded output on B, and what you can do is to transmit communicate with this input process. And so what you end up getting is this process. And this all happens in one step in our new operational semantics. And on the other hand, you cannot reduce this process because even if you take off this tau prefixing, the communication you can do is a communication with this and this, but you will end up with an unguarded output, which has no opponent to communicate with. So in our new reduction semantics, these kind of rules, these kind of process cannot reduce. And what we showed in our recent FSCD paper is that processes modulo barred congruence, which is defined using this reduction relations, form a compact closed Fried category. Well, this is just a fancy way of saying that it satisfies the equational laws I presented in the first part of my talk, meaning that not only is a problematic either rule, but it also satisfies the generalized beta rule. Okay. So one might think that reduction semantics is too strange, but actually the conventional reduction can be simulated by adding tau prefixing in front of all the output actions, because a conventional reduction can be mimicked by this reduction, since what you can do in this process is to take off this tau prefixing, and the only thing you can do is a one-step communication, and after that you will always end up with a process that is guarded by tau prefixing. So in that sense, okay, so the new reduction semantics is a bit strange, but still you can simulate the conventional reduction. But this does not mean that various equivalences are also preserved by this translation, because context not in the image of the translation have additional observational power. So, well, what we wanted to do by this research is, one, to check whether there is an actual operational semantics that has a good match with the categorical semantics. And few very informal insights that you can get from this work is there is this mismatch between synchronous and asynchronous, in the sense that it seems that synchronous communications seem to have a better match with the denotational semantics. And this is also observed in the studies of game semantics. But if you look at the grammar of the asynchronous picalculus is convenient to work with, because you can think as output as function applications. And I would say that this discrepancy is another difficulty of giving denotational or categorical semantics against the picalculus. And okay, so we did introduce a slightly non-standard reduction semantics, but picalculus with a new operational semantics might be a good meta language, because it has a better match with the categorical semantics and can still imitate the conventional operational semantics. On the other side, the new reduction relation does not have a good label transition system, which means that it is really hard to do some operational reasoning using the new operational semantics. And well, for this reason, the idea of using this new calculus as a meta language might not work, but I think it's still a direction that we can try investigating. Okay, so now let me wrap up my talk. So, what I did is we established a correspondence between a variant of a picalculus and a compact closed Fried category. So we did give correspondence, but actually in giving this correspondence, it kind of gave us some insights on why it is difficult to give a categorical semantics to the picalculus. And as a future work, I want to investigate the relation between compact closed Fried category and linear logic. Also investigate the relationship against session typed calculi through this relationship. And I would also like to investigate on the eta rule and give a further investigation on the eta rule and the new reduction relation we defined. Another thing that might be interesting to do is to investigate the power of non-replicated inputs, which we omitted from our calculus. I think it is a kind of a folklore that non-replicated input is a source of like the imperative power of picalculus, but I have never seen a paper that actually state this result. So it might be interesting to investigate the relation between reference cells and non-replicated inputs, and also see whether it can we can add non-replicated inputs also to the denotational world. Okay, so thank you for listening. I'll stop speaking and will be happy to answer to questions.
Thank you, Ken. So I'm unmuting you all so we can clap. Okay, yes. So thank you, Ken. So are there any questions? Okay, I've got a probably rather like naive or stupid question. I might have missed a point, but well, how the restriction to replicated inputs help getting the categorical semantics?
Okay, so let me go to the very first point. Basically, the starting point of our work was to consider that, well, replicated inputs are functions. And usually functions can be used multiple times. So that means it needs to be replicated in some sense. And well, if you add non-replicated inputs, it means that there is a function that you can only use one time, and that complicates the denotational semantics, and I'm not really sure how to model non-replicated input. So we basically gave up because it was difficult.
Okay, I see. And then it seems sorry, I'm missing. So they have any like vague idea how
okay, how to overcome this?
Yeah.
Well, okay, one thing I can say is probably that non-replicated input for linear names, meaning that names that is ensured that you can only use once by the type system, is probably not easy, but it can be modeled using denotational semantics or categorical semantics. But so in this sense, I think there is, I mean, some non-replicated inputs can be modeled using categorical semantics. But the difficult part of the general non-replicated input is that there's a mismatch between the type and the use of the name. I mean, the type says you can use it many times, whereas the actual use of the processes is only one shot. And I'm not really sure how to overcome this mismatch. And as I said, adding non-replicated input, by adding non-replicated inputs, you can you get the power to encode like things like reference cells. And even in the functional world, I think giving a clear categorical semantics against reference cell is something that people have difficulty with. So I think it's really hard challenge to give a categorical semantics against the general non-replicated input.
I see. Thank you. Yeah, maybe the direction of research has connection to the investigation on linear logic in relation with this categorical semantics, but I don't know. So is there any question? Are you all happy with? And yeah, I quite enjoyed your talk, and like especially the honest presentation of what could have been done better, you know. So I really enjoyed the talk. So okay, I think it's time to finish this session. So let's thank Ken again by the clap. Yep. Okay, so let's thank Ken again. Thank you. Okay, I stopped recording now.